week of data science development series. This week we have a good one for you. It's going to be search and relevancy. So, anytime that you see the search algorithms or actually just doing search in your everyday life, maybe you'll get some insights today on how that is operating in the background. And Trey's going to be able to show you exactly how that happens. So for those who aren't aware, and it's your first time at Data Science Development Series, this is a 6-part series that we're offering to introduce the kind of typical topics that data scientists see. It's every Wednesday night from 5:30 to 7:30 or 7 o'clock, just an hour and a half. We've already done sessions on machine learning. We've done sessions on natural language processing 101. We've done a session on computer vision. And then we've also did a deep dive into deep learning as well. So now this is going to be our 5th episode. Next week, we'll be capping it off with Khalife presenting on recommendations. So I do want to, I am your host if this is your first time, Brian O'Connor, Director of Data Science at Pandera Systems. Pandera Systems is a sponsor of this series alongside TAB and Southern Data Science Conference. Pandera Systems, who I work for, we're a data analytics firm, consultancy agency. TAB is event-based, community event-based organization, which Tommy's the founder of. So you'll see Tommy on everyone who's kind of been presenting has been part of that community. Really what they do is they host community events, typically outgoing drinking a beer. It stands for Tech and Beer, but they also sponsor these type of digital events nowadays. And then Southern Data Science Conference, which Khalife is founder of, who you'll hear from next week, and he's also on the panelist session today to do any type of answering of Q&As, jumping in if needed. Southern Data Science Conference is a conference specifically for data scientists, where people in the research community as well as the community just as a whole come together and share topics, and they have conferences in the Southeast each year. Now with that, I'll hand it over to Trey Grainger. So he's founder at Searchkernel, and he's going to teach you about search and relevancy. Couldn't find a more perfect person for this.
Awesome. Thanks, Brian. Let me get a screen share over here. And all right. All right. Excited to get going. As Brian mentioned, I am Trey Grainger. I'm the founder of Searchkernel, which is a search, consultancy software development company that helps people with search and relevancy problems. I am the former Chief Algorithms Officer at Lucidworks and their SVP of Engineering. They're a large company building intelligent search applications for many of the Fortune 1000, formerly a career builder. I am an advisor to Presearch, the decentralized web search engine, as well as author of the book AI Powered Search, which is in development, and co-author of Solr in Action. And with that, I will talk about our agenda for today. So we are going to break this into 4 parts, I guess 5 parts with the Q&A. Keyword search in the inverted index, relevance ranking functions, user signals and reflected intelligence, understanding user intent, and then questions at the end. This is not intended to be a sort of intro to how to do search. This is more of an overview of the field of search and relevance to really give you a feel for what search is, how it works, and what kinds of things are possible. Of course, if you want to dive in and get started, there's lots of tools for that, and I can point people to those as well. But I wanted to give people more of a survey of the field of search and information retrieval. So starting out, we'll talk about keyword search in the inverted index, which is the beginning of a typical search journey. So the first question I would ask, and many people will ask, is why do I need a search engine? We've got databases. Why can't I just use a SQL database? And so if you think about the questions that people ask, let's say somebody had a set of documents that they wanted to search through. So in this case, the query they want to issue is buying a home, and the documents they could search through. Over here on the left, I've got a list of potentially relevant books. So, the Beginner's Guide to Buying a House, Purchasing a Home, Buying a New Home, etc. These are the titles. And then over here on the right, I have some irrelevant books. So A Fun Guide to Cooking, How to Raise a Child, Buying a New Car. And the task at hand is, how do I find the content that actually matches my query intuitively? And so if I tried to do that with a database, you could certainly try. I could do a select star from books where the name is Buying a New Home. And I would get exactly 0 matches because none of these documents contain this exact text. And then all the documents would be non-matching. So I could look at that and say, okay, well, let me modify this somewhat. That didn't work. Let me do a more a fuzzier query. So in this case, I'm going to search for each of those words, but with a like. So I just want to scan the text and find any of them that have buying and a and home. And so in this case, I would find one book which has buying and a and home in it, and then all these other books would be non-matching. Not only that, but I'm not using any kind of an index, so this is actually taking quite a while to run because it's essentially scanning the entire table of books. So that doesn't really work either. I could get even more fuzzy, and instead of requiring every document to match, I could just say any document that has any of these words. So anything like buying or a or home. And of course now I match almost every single document, every single book, because any book that has at least the word a in it is gonna match. And then of course I've got this one document that apparently doesn't have any of those words, but actually if you look at it, it's about buying a house. So it actually would be a highly relevant book, but it doesn't come back, and essentially everything else does, whether it's relevant or not. So that doesn't work either. And assuming I could even craft a query or use a feature in my database that allowed some sort of naive text searching, I still have the problem that if I could craft that query and somehow prevent scanning the entire table, which if I start to get to millions and millions of documents, is going to be painfully slow. I still have the problem of relevance, which is once I've found the documents that match, how do I bring them back such that the first page of search results gives me the best documents, the ones that are the most relevant for the query that I'm running? And so that's where search engines come in. So search engines are optimized for essentially 3 things. Very fast matching, so taking queries and executing them in milliseconds. Relevance ranking, taking potentially millions or in some cases billions of matches and bringing back the most relevant ones at the very top so that somebody only has to look at the first page and ideally only the first few results. And then horizontal scaling. So on the infrastructure side, making sure that, whether I have 10 documents or 10 billion documents or even 10 trillion documents, that it's possible to search on them, very quickly find the answers, and then rank the results. And so that's where search engines, sort of combining these 3 things really shine. And there's essentially, and I'm only going to talk about open source search engines in this presentation, just because there's some good options out there, and this is probably what people will get started with. There's essentially 4 engines I'll point people at that you could leverage. Apache Lucene is an open source search library that allows you to build Java-based applications that have search capabilities inside of them. It's not really a search engine per se. It doesn't scale horizontally and do all of the things you would expect a full search engine to do, but it is a core library that enables search. And 2 of these options I have on here, Apache Solr and Elasticsearch, are actually both built using the Lucene search library. So as a result of that, a lot of the capabilities in Apache Solr and a lot of the capabilities in Elasticsearch will be the same, or at least function very similarly because they have a sort of shared library that they both use. Apache Solr is completely open source, part of the Apache Software Foundation. Elasticsearch is partially open source. Portions of it are open source Apache license, portions of it are under a proprietary license but free to use, and portions of it are paid. So they sort of have a freemium model going on there. And then Vespa is a more recent addition to the open source search landscape in the last few years, they tend to really focus a lot more on the sort of vector and tensor and machine learning side of things. So a lot of good options to choose from. I'm personally tend to do most of my work in Apache Solr. And so that's what I'll be using today as a basis for discussion. So the Solr's website, it's the popular, blazing fast, open source enterprise search platform built on Apache Lucene. You can download it, play with it, run it, and get started today if you want to. And so in terms of search features, there's a lot of things that search engines do beyond just matching and ranking of results. This picture over here shows you an example of some of those things, but we have things like multilingual keyword matching. Regardless of the language, we can match on keywords and phrases and try to understand them. There's relevance ranking of results, which we talked about, faceting and analytics. So when you run a search, being able to see aggregate information about categories and titles and numbers and ranges and those kinds of things. There's hit highlighting, which is when you run a search, actually seeing a blurb of which text was matched, so you can figure out if it was a good match that you maybe want to click on. There's spell correction, autocomplete and type ahead in the search bar, sorting of results, grouping results based upon some shared key if you've got duplicates. We talked about scalability, so a search engine is going to be distributed and fault tolerant, so that it can run in a cluster to support again billions or trillions of documents as needed. There's capabilities like geospatial search for sorting based upon distance, or filtering based upon a radius or something like that. Complex function queries to be able to craft custom relevance functions. Recommendations, using, finding more documents like a specific document, the ability to do graph queries and traversals, support for SQL queries if you need it, and then a lot of batch and streaming operations that really support things like machine learning and so on. A lot of other capabilities as well, but more just want to share the slide to give you the sense that the search engine itself is mostly focused on matching and ranking. That's what we'll talk about today, more from a data science standpoint, but there's lots of out-of-the-box features that you would expect a search engine to have. And if you're taking your content and putting it into something like Apache Solr, you have access to all of these capabilities. And so the question, we talked about scalability earlier and execution of queries very fast, is how does Google index over 60 billion pages in a few milliseconds? I think the number's larger than that, but the estimate's about 60 billion real pages in Google. When you run a search, how is it possible that it could go through all of those documents and return results in 10 milliseconds or so? Of course, the answer is that they pre-compute the answers. So they're not actually scanning through all of those documents in real time as you're searching. They've taken those documents, broken them apart, created indexes, and they can essentially go look up the answers to your questions and return them, with a little bit of relevance ranking involved. And so the way this is done in a search engine is leveraging a structure called the inverted index. An inverted index essentially flips the idea that you would typically have in a database of on its head of an ID for a document mapping to the content of the document. And so over here, this is how I might represent a document if I'm just putting it in a table in a database, where I've got some ID that represents the document and then some field that contains the content. So in this case, I've got document 1 with the text, "Once upon a time in a land far, far away," that is filling the content field. Document 2, "The cow jumped over the moon," etc. What an inverted index does is it actually takes the content that's in the document and it tokenizes that content and splits it apart into individual keywords. And then it creates an index that maps those keywords to the list of documents in which they appear. And so what you can see over here is that the word brown is in this index, and it's possible to look up the word brown and see that it exists in document 3 and document 5, which are this document here, brown, and document 5, the brown cow. And so now, if I want to run a keyword search for the word brown in my index, all I have to do is go look it up, and I immediately know which documents it appears within because of this inverted index. There's no additional processing necessary. And this is how search engines are able to be so fast at looking up search results. So of course, in order to get these documents into the inverted index, I have to take that content and actually split it apart. That process is known as text analysis. And so, in this particular case, I've got some text here, looks like a tweet, Yum, drinking a latte at Cafe Greco in San Francisco's historic North Beach, etc. In Lucene and Solr, what I would do is I would configure an analyzer for this field for tweets, and I would set up three things. I could have something called character filters, which essentially allow me to clean up the text before processing it. I can have tokenizers, and tokenizers take the text and actually split it up from one string, the entire tweet in this case, into multiple individual tokens or keywords. And then once I've tokenized the text and split it apart, I can run 0 or more token filters. And the token filters is essentially take tokens and process them and do things like filter them out, adjust the text, or what have you. And so in this case, I've essentially got, I've got this handful of filters defined. This first one essentially splits words based upon, mixed case and things like that. The second one, called the stop filter, removes stop words. So you can see these words that are X'd out. A lowercase filter takes all of the incoming text and takes it from mixed case to lowercase so that it's in the index. I remove accents, and then I do a little bit of stemming, which is taking English words like plurals and like engineers and mapping it down to engineer so that both words, the word engineer or engineers, will actually match any document that contains either one. So this analysis process runs both on my documents when they go into the search engine to create these tokens that go in the index, but then also whenever a query is run later, the query text is run through the same analysis process so that any token that I would insert into my index from some text I would actually at query time generate the same token from the same text so that I always have a match in my index. And it's really important that both the index side analysis and the query side analysis always resolve to the same tokens, and that's how you have a match when you look up against the index. There's lots of different capabilities for analyzing text. In my book, Solr in Action, I include 32 different language configurations for, different languages and how they're handled. So this could be Japanese, Hindi, Greek, English, Persian. You sort of like go through the list and you can, configure different analysis chains to very specifically be able to handle each language. And so that's the process of taking content and putting it into this inverted index in the search engine so that I have the ability to then search on the content. What happens at query time is, like I said, I will take my entire query for, in this case, apple juice. So I've created a collection in Solr of documents that are related to food. I've indexed them using that process we just discussed. And my inverted index now has a lot of keywords inside of it that have been pulled out of my content. At this point, I want to actually not just search for an individual keyword, but actually multiple keywords. So if I run a search for apple juice, what actually happens in this case is, like I said before, I go and I look up apple in my index, and I immediately have the list or the set of all documents that contain the word apple. I then also go look up juice, and I find the set of all documents containing juice. And then, of course, if I just want to return the documents containing apple and juice, all I have to do is a set intersection of those two sets that I just looked up, and I can derive the set of documents that contain apple juice. And so once I've done that, I now have the ability to take that set of documents that is my answer for all of the potential documents that match my, my query, and then I have to score them. And so that's where relevance ranking comes into play. And so in general, once I've matched these documents, I've got this query, and then in each of my documents, I have a bunch of text, and I'm trying to score how well each of those documents and the text within them matches my query. So essentially what happens, this uses sort of a vector similarity model where I build a vector, which is a list of the, all of the terms that are in my query. And then I, get a score for those same terms in my document. And I calculate the similarity between my query for, in this case, apple juice, and each document and how well it represents apple juice. And then this cosine similarity between them, if you sort of remember, definition of cosine, if two vectors are exactly the same, then they're going to have a cosine of 1, meaning that it's a perfect match. And if they're very different or not very similar, then that score is going to be closer to 0. And so we use this sort of vector similarity calculation to determine the relevance of the documents as they relate to the query that was run. And so if you tuned in last week to the NLP session, then you'll know a good bit about TF-IDF. I am not going to spend time too much going into the mechanics of it today, but just it is a very high level understanding. TF-IDF is the core metric that is used to rank the similarity between keywords between documents and queries. And so TF stands for term frequency, and it's essentially a measure of how well a term describes a document. So if I find a document, I'm trying to score it relative to the query, and the query has the words apple juice in it. Term frequency is essentially a count of how many times the word apple appears in that document, and then for juice, how many times the word juice appears within that document. And if I just look at apple for now, say I had a document with the word apple appearing in it 10 times versus a document with the word apple appearing in it 1 time, I would generally expect that the document with apple appearing 10 times would be more relevant for my query than the document with it only appearing once. So term frequency is one piece of the calculation, but then the other piece is this idea of inverse document frequency, which is a measure of how important or specific a term is overall. And essentially it's how rare. So if somebody searches for a query like this here, at the bottom, the cat in the hat, then I would expect, if somebody ran this search and all of the results that came back on the first page of my search results were only documents that had the word the in them, because again, I'm scoring the cat in the hat. If somebody only saw documents containing the word the or in, they would probably be pretty unhappy with those search results. And the reason or intuition there is that the word cat and the word hat are a lot more specific and a lot more important to that query. So what we really want to do, if hat is the most specific or rare, we want to score documents containing the word hat higher than documents containing just the word the or in. And we want to score documents containing the word cat higher than the or in. And documents that contain cat and hat would get an even higher score because we would add up the term frequency and times inverse document frequency of each of the words in our query and get a score that way. And so that's sort of basic TF-IDF. If that's new to you, I would encourage you to go watch the NLP session from last week. But with that intuition, that's essentially the core of how the search engine works. We go look up all the terms that were in our query in the inverted index. We do a set intersection. We find the documents that match, and then we use this TF-IDF score to rank each document based upon how well the keywords in it match the query, again, using TF-IDF. In the search engine, in Lucene, Solr, Elasticsearch, it's a little bit more complicated than that. So this is the actual default relevance ranking algorithm for text. It's called BM25, and it contains a lot more parameters, which I'm not going to go into today. But you can still see that essentially for when it's trying to score any given document for a query, it takes all of the terms that were in the query and generates a score for how well that term is matched. And you can see here that term frequency with some modifications times inverse document frequency for each query document pair, or sorry, for each term in the query is ultimately how we calculate it. So it's still TF-IDF based. There's just some modifications here that may make a lot of sense in search engines. And so I've got a Jupyter notebook I could pull up to kind of demonstrate some of this, but I think I'll just stick in the slides for now, and I can pull up notebooks later if we want to during the discussions. But you know, in general, if I've got an example here where I've got 3 documents that all have the words the, cat, in, and hat in them, then if you sort of intuitively look at these, document 1 is the worst match intuitively. The interesting thing is that the person in the wrong made the right decision in the end. That actually doesn't contain cat in the hat at all. It just has effectively the word the and in it. Document 2, which is the best match. My favorite book is The Cat in the Hat, which is about a crazy cat who breaks into a house and creates a crazy afternoon for 2 kids. And document 3, which is an okay match. My neighbors let the stray cat stay in their garage, which resulted in my favorite hat that I let them borrow being ruined. So it's not a match conceptually for The Cat in the Hat in the sense that it has nothing to do with the book, but it does essentially contain all the words. So it's, you know, the search engine doesn't necessarily know the difference natively. And so if I send these to the search engine and then I go to, you know, look at the BM25 score, then, you know, if I query the search engine for the cat in the hat, then I can actually ask it to explain the similarity calculation. And it's that algorithm I showed you on the last page that we're not going to go into. But essentially what I get back is, you know, document 2 gets this score, 0.687. If you remember, document 2 was the best one. Document 3 gets the next highest score. It contained all the words, but it wasn't the best match. And then document 1, which didn't have cat or hat in it, got the lowest score. And so you can sort of see the algorithm working, and then that's the relevance ranking that you would get back from the search engine for this query. One thing to sort of mentally keep in mind is that when I run that search for the cat in the hat, even though we think of it as one query, internally what the search engine is doing is effectively creating a vector where the you know, the entries in the vector or the dimensions of the vector correspond with the individual keywords that I passed in. So another way to think of it is I've created a vector I'm searching for where the first entry in the vector is the BM25 or keyword text ranking score for the term the, followed by the, you know, keyword ranking score for the term cat, followed by in, followed by the, and followed by hat. Since I've repeated the twice, it's in here twice. In Solr, to run the query explicitly like this, I could actually just say I have a function. My function is a query function, which returns back that score. And then I essentially have 1, 2, 3, 4, 5 elements in my vector. And then that vector, again, if you think of it from a cosine similarity standpoint, I am you know, matching between the query vector and the same vector in my documents. And you can see that when I break it up like this, I actually get the exact same scores that I saw before on my last screen when I just searched for each term individually. So the point there is that a function is being applied to each of these words that gives it a score. And when I add up the score for every term in my query, that's how I get my relevance calculation. And so that's the sort of high level understanding of how search engines match documents very quickly with the inverted index and how they rank those documents based purely upon the text and the statistics around the text that are in the index. And that's great, but the problem, if you only go that far, is that you are completely missing any understanding of domain-specific knowledge. So for example, from a ranking standpoint, if I was building a news search engine, then I happen to know that things like the popularity of the news article or the freshness or sort of how recent the article is are 2 of the things that primarily drive relevance. If I'm building a restaurant search engine, things like geographical proximity, how close is the restaurant to the person running the search, and maybe price range sensitivity are critical. If I'm building an e-commerce application, the likelihood of a purchase, so based upon what I ran a search for, what are the things the customer's most likely to purchase is key. Movie search, popular titles are generally more relevant. For job search, things like the job category, the salary range, and geographical proximity tend to really matter. And so, you know, the TF-IDF score or BM25 score that we just looked at of keywords are useful as a base, as a default, but they can't really hold their own against good domain-specific relevance factors. And so just as an example, let's say that we have a bunch of users of our search engine, and these sort of correspond to user profiles that I might have. So say this is a job search engine. And I've got somebody like, John, who lives in Boston but wants to move to New York, or maybe another big city. He's currently a sales manager but wants to move towards business development. If I can build out an understanding of my users, then instead of requiring them to explicitly go in and type in keywords, I can actually construct queries that represent their intent or represent our understanding of them and run that query as a search. So in this case, I'm going to take Jane just as an example. She's a nurse educator in Boston, seeking between $40,000 and $60,000 a year in pay. I can actually take Jane and using the flexibility of the query syntax in the search engine, without having to write code to build a model and sort of build my own recommendation engine code, I can essentially say, all right, Jane's a nurse educator, so I'm going to search on the job title field for the exact phrase nurse educator with a very high relevance boost, or as long as at least one of those words appears in the title, or maybe they both appear but not as a phrase, then I'm going to give it still a high boost but not as high as a perfect match. I'm going to take Boston and say that if I match in the city of Boston and the state of Massachusetts, I get a really high boost. Otherwise, as long as the job is at least in Massachusetts, let's return it. And then finally, if the job falls within the range of $40,000 to $60,000, I want to apply a boost on that document so that it shows up higher in the search results. It's not a strict requirement; it's a fuzzy sort of requirement where it just makes the results show up higher. But ultimately, if I can construct this query and run it against the search engine, it's a fuzzy match, and what I get back in terms of relevance ranking are these three documents. So in this first case, I've got a clinical educator that is in Boston between $40,000 and $60,000, so good. The second one is a nurse educator in Braintree, which isn't an exact match for Boston, but it's still in Massachusetts. Salary also falls within the $40,000 to $60,000 range. And then finally, I've got a nurse educator, good, in Brighton, again, not Boston, but still in Massachusetts. And in this case, the salary actually falls outside of the range, but it's still a match because the salary wasn't a requirement, and it was a fuzzy match where we were really trying to influence the ranking. And so what we've essentially done here is created an attribute-based recommendation engine using the search engine and its ability to match on tokens and rank as the mechanism for delivering that, by essentially turning our understanding of Jane into a query against the search engine. Going back to our news website example from earlier, and again, don't worry about the syntax here because if this is new to you, this is going to be hard to read. But what I'm essentially showing you is that if I'm running a news website and building a search engine for the news articles, I can structure my query in such a way that 25% of the relevance is going to come from that BM25 keyword score, the TF-IDF based ranking we talked about earlier. 25% of my relevance is going to come from how close that article is to the person running the search. So if it's a local article, then it's going to show up higher for that particular user. 25% of my relevance is going to come from the publication date, so how recent the news article is, and 25% of it's going to come from the popularity of the article. A very popular article in my hometown that was just published and matches my keywords is going to get the highest score, and then in a sort of fuzzy matching way, everything will kind of cascade down from there. And so, in this case, I search for basketball, and this is my location. I would expect to be able to, use this to have a very domain-specific relevance function for matching and ranking my results. And again, this can all be executed in, typically milliseconds or tens of milliseconds. And so those are the sort of essential pieces for how we think about relevance from a, using the search engine to model relevance standpoint. With most search applications, people start down here at what I call the bottom of the search intelligence spectrum. And so, keyword search, TF-IDF, BM25, text analysis, these are the things you get out of the box with any of these search engines that we talked about earlier. Usually once people have deployed them, however, they realize that There's certain words that don't match as you would expect, and some of the ranking is off, and it doesn't really have a good understanding of the rules of the business you're operating in. So people start to build those things out as taxonomies and doing entity extraction and those kinds of things on their documents, on their queries. Eventually, people realize that even that is not sufficient, and they start focusing on building much more complex models for understanding the query intent of the end users. So doing things like query classification, semantic parsing of queries, leveraging things like thought vectors and embeddings, which we'll introduce in a few minutes, doing semantic search, knowledge graphs, trying to build question answering systems, introducing clustering and other machine learning techniques, and so on. Eventually, people get to the mode where they realize that this relevance tuning is hard, and they start trying to automate as much of it as possible through more sophisticated A/B testing models, things like multi-arm bandits, which automatically adjust the percentage of traffic going to particular relevance algorithms based upon how well they're performing. Things like genetic algorithms or machine learned ranking, where you actually build what are considered ranking classifiers, which are able to take to automatically learn what kind of parameters matter for users to match any particular document. So for example, in that news use case we had a minute ago, where we had 25% of the relevance focused on each of the 4 categories, using something like learning to rank would allow you to automatically learn what those weights should be and what other categories might matter. And then eventually, people start to realize that a lot of these capabilities can actually be completely automated from a learning standpoint by leveraging some of the techniques we'll talk about in a few minutes for automatically using your content and using the user interactions with the search engine to learn how to do all of these things and make the search engine more intelligent. And so that brings us to the idea of reflected intelligence. Reflected intelligence is the idea of creating feedback loops within our search engine such that it can be constantly learning and improving and adjusting based upon real user interactions. So search engines are one of the more fun areas to work in data science, in the sense that we have sort of a live test bed where we can, make some changes, put them in front of users, immediately see what the users do and get feedback, and then use that to build models and improve those models. And we have this sort of closed loop system where we can be constantly improving and trying things. So with reflected intelligence, it's very simple. A user runs a search, they see some results, they take an action on those results. Maybe they click on a result, maybe they, if it's an e-commerce example, maybe they add it to their cart, if it's a product, or purchase it. Or in some cases, maybe they bookmark it or download a file or something. But we record all those actions, and we refer to each of those actions as a signal. And so we'll talk about signal processing in just a minute. We then build models that allow those actions to be to inform the system, and then those models go back to make future searches better. So as a concrete example here, somebody searches for the word iPad. I record all of the people who search for iPad. Here's the query, and then I record the results that they saw as in response. Then the user takes some action. So maybe they click on a document, maybe they purchase a document, etc. Those actions then run through an offline process typically that will process those signals and build machine learning models that and those learned relevance models can then be deployed back into the engine to create this closed loop system. And there's essentially 3 categories. There's more you can break down, but I like to think of reflected intelligence in terms of 3 key categories for types of reflected intelligence. One of those categories is known as signals boosting. Signals boosting is a form of popularized relevancy, which means that it takes your most popular queries that get the most traffic and the most sort of document interactions, and it automatically learns which documents are the most relevant for each query based upon what users actually are interacting with and prefer to see. Learning to rank, in contrast, is a form of generalized relevancy. So instead of learning specific documents that are the best answers for queries, it is able to learn the attributes associated with those documents that matter. And so in this case, I can learn a relevance model that can be applied to any future searches and any future documents, because the model has learned the features or attributes that matter as opposed to the specific document IDs that matter. So it's a way to generalize my relevance ranking function and learn it. And then this last category is collaborative filtering, which is the ability to deliver personalized relevancy. So collaborative filtering, typically is used for recommendation engines. It's the idea, users who purchase this product also purchase these other products, or users who liked this also liked that. There's multiple types of collaborative filtering, which we'll talk about in just a second. And so when I think about my signals boosting model, this diagram should look very similar. It's the same reflected intelligence feedback loop. But what happens with signals boosting is that somebody searches for the term iPad. I log those searches. They see the results. They take some action, same signals as before. They click on some things, purchase some things. I run a signals aggregation, which essentially applies a function to these signals to automatically learn that for this particular query, this document gets the highest score, and then those boosts go back into the system, so that the next time somebody runs a search, we automatically boost the document. When someone searches for iPad, we automatically boost the documents that matter the most for them. So as an example, if I create a search engine, put a bunch of products into it, which are my documents, and then just run a search for iPad, using just text and BM25 scoring, I'm going to get results that look like this, because iPad is in the name here and iPad is in the name here. And because the word appears multiple times, therefore these documents rank highly, even though you can look at these and tell that these aren't iPads, these are accessories for iPads, but the search engine doesn't know that because these are just, it's just looking at the text and the keywords, and it happens to have the word iPad in it many times. Once I apply my signals boosting model, though, to automatically boost the documents that people tend to interact with and prefer, now my search engine has automatically learned from essentially a crowdsourced relevance function that when somebody searches for iPad, they actually want to see these products, because that's what the actual aggregate user behavior tells us. So that's signals boosting. The next type of reflected intelligence algorithm we mentioned is learning to rank, which is that generalized relevance model. And so in this case, it's a little bit more complicated, but the same general flow. Users run their search for iPad. We record those users, see some results. They take some action. We record those. And then at this point, we run a process, a machine learning process, to build a ranking classifier. That ranking classifier allows us to learn which attributes matter, and essentially build a ranking model that will allow us to, next time somebody runs the search for iPad, even though the TF-IDF or BM25 ranking function would return documents in this order, we can then take those results, pass them to this ranking classifier, and then get a resorted order based upon a much more sophisticated machine learned ranking function. And so then I can essentially take any future search and rank it based upon the same factors that tend to generally matter within my domain, and then I get much better results because of that. And then finally, we've got collaborative filtering, which is the personalized relevance. So in this case, I run a search for iPad, record the signal, users see results, take some action, and at this point I'm doing some matrix factorization to try to automatically figure out, in this case, that Alonzo as a person, if I'm going to recommend some items for him based upon his behavior, then these are the items that I might recommend, and here's the relative weight, and I give those recommendations back. I could alternatively, instead of recommending items for Alonzo, a user item recommender, I could do an item to item recommender to say that, for document number 22, the best, other document is, document 12, for example. And there's multiple different ways to do this collaborative filtering, but it allows me to learn the tastes and preferences of people and how those tastes and preferences map into factors associated with my content, so that I can then also either map the users to items or map items to each other based upon those factors. And then there's many other kinds of reflected intelligence models. They typically all fall into those same categories of, signals boosting, collaborative filtering, or learning to rank. But just as an example, this first one here is the user item recommender we just talked about. The second example, though, is actually learning a personalized profile of a user from the from their behaviors and actions. So I can see, for example, that for Alonzo, he was searching for tablets, and within the category of tablets, he was mostly looking at black 32 gigabyte devices that were made by Apple. And as he sort of expands out and looks at other categories, we can combine that understanding in such a way that we can more or less try to figure out what Alonzo's preferences are, so that in the future, when Alonzo searches for something, we can take those into consideration or use those to help match him to something else. This third category is item-to-item recommendations. So, document 22 is a perfect match for document 22, of course, but also document 12 is the next best match for document 22, because the users who interacted with doc 22 also tended to interact with doc 12 more so than with other documents. And then finally, this last example is recommending documents for a query. So given this query, recommend these documents. This is very similar to the signals boosting model that we talked about earlier. And you could think of lots of other ways that you could essentially have a graph here of relationships between users and items and what have you, and then use these to help inform the relevance of the search engine as it's matching. So quick summary of reflected intelligence. 3 kinds of models here. There's signals boosting, which ensures the most popular specific content or documents for a query return first, a form of popularized relevance. There's learning to rank, which learns a model of which combinations of features generally matter most across users, and ranks all content and answers using that model. Form of the first one is popularized relevance, and learning to rank is generalized relevance. And then collaborative filtering, which learns which items are best to recommend to a given user or related to a given item based upon behavior of other users who have previously interacted with similar items. So that's reflected intelligence. And that's when we talked earlier about creating a more intelligent search engine that can be self-learning and can sort of auto-tune itself. Reflected intelligence is one of the key ways that we do that, by leveraging user interaction and feedback to crowdsource our understanding of relevance and have the engine automatically tuned based upon user interactions. But then there's this notion of understanding user intent. And so the ultimate goal of a search engine is when people run searches, to understand their intent and then to bring back the content that best matches that user intent. We don't want to bring back irrelevant documents for users, and we don't want to bring back documents for users that match the keywords but aren't what they intended given their context. And so there's essentially what I think of as 3 dimensions to user intent. One is this content understanding dimension, this blue circle. And that's, what data do I have? What are the keywords? What are the fields? What can I understand about that? The second dimension is this user understanding dimension. And so this is, given my users and their behaviors, what can I learn from those? And how can I use those as context to help me understand the user intent? And then the third dimension is domain understanding. And so, this is really understanding, what are the terms and phrases and entities in my domain? If I've got, for example, a product search engine, how do those products relate to each other? What attributes do they have? What are the different, are there, companies or manufacturers or other entities or titles, and just really understanding within my domain, what do all these terms and phrases mean and how do they relate? If you sort of look at the intersection between these, something that's only content understanding would be essentially a plain text keyword search. No understanding of the domain context and no understanding of the user context. Something that is pure user understanding, but neither of the others, would be something like collaborative recommendations, where I'm recommending items to people based upon what other users have done, but I don't actually have any native understanding of how they map to my domain or how they map to the content that's in the documents. And then finally, a pure understanding of the domain but without understanding the content or the user would be something like a knowledge graph, where I've built out a knowledge graph that represents the relationships and what's important for my company, but I haven't related them back to these other contexts. And then, of course, if you start to look at the intersections between these, if I look at the intersection of content understanding and user understanding, I get personalized search, where instead of explicitly typing in keywords and trying to match based upon those, or using a pre-built understanding of a user and matching based upon that understanding, but without user input, I'm actually using my understanding of the user to run the user's keyword search, but actually personalize or cater the results to them. For example, boosting based upon documents that are closer to them or things like that. And then one of the more interesting categories here is semantic search, which we'll talk about in just a second, which is the idea of combining my keyword search with an understanding of the domain and the items within the domain. And so that takes us into knowledge graph search or semantic search. And so this is an example query that this is for a search application that I built, where I'm taking a user query for barbecue near Activate. Activate is a search conference that I spoke at last year. And so it happened to be held in Washington, D.C. at I think the Washington Hilton. Just for context here about this query. That context matters. Me as a user, understanding that context would matter. But in this case, I'm just trying to run this query. And so one of the things that I can do is take parts of that query and actually use my search engine as a knowledge graph to go to that inverted index and ask it, hey, given this word barbecue, what is it related to within my content? So this is something called a semantic knowledge graph. And essentially what I'm doing is I'm taking the word barbecue, and you can ignore the syntax here, I'll explain it to you, but I'm taking the word barbecue and I'm saying, hey, search engine, please tell me the top 2 categories that are the most semantically related to this keyword barbecue. And then within each of those categories, I want you to bring me the top 3 or 4 words back that are the most semantically related to barbecue within that category. And so what I get back here is that the term barbecue is most related to the restaurant category. And within the restaurant category, it means it's most related to things like brisket and ribs and pork. And then if I look at the next category, the next most related category is outdoor equipment. And within the outdoor equipment category, barbecue means things like grill, charcoal, and propane. And so these essentially create 2 distinct, not completely distinct, but somewhat distinct meanings of barbecue. The first being a sort of a type of food or meat that somebody might eat. And the second being a type of device, which is a grill that has the components like charcoal and propane that make it operate. And so I can take a nuanced understanding of the word barbecue by mapping it into a specific context and then getting a specific meaning within that context. And so that's a semantic knowledge graph, which is able to automatically infer meaning of terms and phrases based upon other related terms and phrases. But the other kinds of knowledge graphs that people are more familiar with are more explicitly built knowledge graphs, where I might have specific items or entities or locations or what have you. And so in this case, I've built out an explicit knowledge graph where I've got a list of entities over here. Just for reference, in that list I've also got places, but my list of places is over here. And I've crawled some text content associated with restaurants and product review websites. And so if I go back to my query, barbecue near Activate, what I can actually now do is I can say, okay, I know barbecue is a term that I've never seen before. I just need to go look it up, but near Activate, if I look in my knowledge graph, I can see the word, that the word near is listed as an entity. And in this case, it actually is indicative of a location distance. So what would happen here is that near would indicate that whatever comes after it might be associated with a location. And so I essentially then go look up and say, okay, I'm looking for near, and the word activate, I need to see if it's associated with a location. So I can then look up activate, and I can see that activate is a conference, that is an event that has an entry that indicates it's located at a venue. And that venue is located at a hotel, and that hotel has a specific location, in this case, an address with a latitude and longitude. And so now when I go to run my search, by doing that quick traversal, I can understand that near activate actually means, say a 50-kilometer radius from this specific point. Further, and so, that if I look at how this query is actually resolved, it's initially tagged and parsed, and then my final output of the search engine essentially would become, let me search for documents that are like barbecue, ribs, brisket, that are of type restaurant, because that's the most semantically related type to this query. And then I want to apply a 50-kilometer radius circle around the locations associated with those documents. So I will only return documents within 50 kilometers of the location of activate. And then I will filter down to restaurants and boost based upon matching of keywords that are semantically related to barbecue. And just as one more example here, I've got top barbecue in Berlin. So in this case, Berlin, in Berlin gets mapped to a location. So I've got my location filter here. Barbecue gets treated the same as before, barbecue, ribs, brisket type restaurant. And then top gets understood as an indicator of popularity. And so in this case, a popularity boost is applied so that more popular restaurants, in this case, those documents will come up higher in the search results. And so this is a way to really map from a text query into a bit more of a structured query that represents an understanding of the domain and how to rank documents within that domain. And when we talk about the semantic knowledge graph and knowledge graphs in general, I think it's really important to understand that in the world of search and in the world of natural language processing, that words and phrases don't have fixed meanings where you can just take the word and define it one way and use it that way forever. But really there's a lot of nuance in the meanings. So the word barbecue we've already talked about, but when I search for barbecue near activate versus barbecue grill, my end queries actually look very different, where barbecue near activate again is type of restaurant, and barbecue grill ultimately maps to barbecue grill, propane or charcoal, and in the type of outdoor appliance. And we actually understand that grill is in fact a product category within our knowledge graph. And therefore we can filter on that product category as well. And so that's, when you start thinking about more intelligent search applications that leverage knowledge graphs, this is what, this is sort of how that's done. And so then the last topic that I just want to introduce here, and this is more sort of on the cutting edge of what's being done in the search world now, is this notion of thought vectors. And so you've probably heard of BERT, which is the language model that got rolled out into Google's search engine for about 10% of their searches. I'm not going to read through the article here, but it's a type of language model that enables something called thought vectors in the search engine. And so a thought vector is essentially taking words and phrases like barbecue or grill, the stuff we just looked at, and instead of trying to understand it and relate it to other things in natural language, instead mapping it to a sort of numeric vector space. And so thought vectors, there's multiple kinds. Essentially any kind of any word can be mapped into a vector that it corresponds with its meaning. In this case, I've got a word or phrase embedding where I take individual words or phrases and map them to a numerical representation of their meaning. I can also do a sentence embedding. So in this case, I take a whole sentence and I map it to a numerical representation of the meaning associated with that sentence. I can do a paragraph embedding, converting all of the text in a paragraph to a vector of numbers, or I can generate an embedding for an entire document that represents the meaning of that document. If you think of this just purely in terms of, representing the vector similar to what we did with the inverted index before, I could have a vector for Apple where, at a very coarse level, I could have one dimension in my vector for every term in my index and just basically put a 1 here wherever Apple exists. So this is a vector where Apple is a 1 and then there's zeros for everything else. This is a one-hot encoded vector. If you've, in sort of like data science speak. But what I can then do is if every word that that I, could have in my index is represented as a vector with just, one entry in it, wherever that word is located. If I want to create a vector for apple juice, all I have to do is add my vector for apple and my vector for juice together, and I get my vector for apple juice. And then if I would want to do a multi-term search, for example, for apple juice, my vector now has 2 entries in it. And then I can, similar to what we did earlier with the inverted index, where I took apple and juice, I looked them up, I got a set of documents here, and a set of documents here, and did an intersection. With this model over here, I essentially have a vector that has apple here and juice here. And then when I go to run that search, it sort of does the same thing through a matrix multiplication, which I won't get into right now. But the nice thing about mapping to these numbers, as opposed to keeping things just as text, is that I can actually do dimensionality reduction on them. And so in this case, I, instead of having, a million dimensions in my vector where, I had a million words in my index and, there's a dimension for every word, I can actually compress down to a smaller number of attributes that matter. So in this case, I've gone from that million down to 8. So I've got 8 categories or features corresponding with each term. And in this case, I've got whether or not the item is food, whether it's a drink, whether it has any dairy. These are all food items. Whether it contains bread, whether it has caffeine, whether it's sweet, the number of calories, if they're high or low, and whether it's healthy. So if I take something like apple juice, I can see that it's not food. It's very high on the drink scale. It's very low on dairy, has no bread, had no caffeine, pretty high on sweet, pretty high on calories, and kind of middle of the road on healthy, but tending towards not healthy. And if I go further to something like a donut, definitely food, definitely not a drink, little tiny bit of dairy, a lot of bread, no caffeine, very sweet, very high on calories, and not really healthy. And so if I then take these words, and instead of representing them as text and looking them up, represent them as vectors, where these are the vectors associated with each of those words, I can now do that same cosine similarity that we talked about before, where we were scoring documents and queries and their similarity, but I can do it based upon these vectors. And so in this case, when I search for the vector for cheese pizza and rank it according to all the other vectors, what I find is that the top most similar thing based upon the attributes that we've defined is cheese breadsticks. That's the most similar to cheese pizza, followed by cinnamon breadsticks, followed by donut, followed by latte apple juice, and then the thing that is the least related to cheese pizza is water. And then if I look at green tea, sort of the inverse, the most related thing to green tea is water, followed by cappuccino, latte, apple juice, soda. These seem to essentially be sorted by, are they healthy drinks? So from a healthy drink to a non-healthy food item is more or less how this is being sorted. But what you notice here is that instead of keyword matching, I'm doing more matching on meaning, because the meaning is being encoded within these vectors here. And so that's sort of a toy example. In real life, you're dealing with large amounts of text, and so we use something called vector encoders to do that. Vector encoders essentially take queries and documents, sentences, paragraphs, etc., and transform them into thought vectors or embeddings. Usually these leverage deep learning, which can discover rich language usage rules and semantics and map them to combinations of features in the vector. And there's lots of libraries to do this. And really the field of NLP has drastically evolved over the last couple of years and really given us a lot that is now informing how we build intelligent search engines. So you're probably familiar with Word2Vec, which was released in 2013. It was one of the sort of earliest examples of building word embeddings. Glove came out about a year later, Fast Text in 2016. And then in 2017, there was this idea of a transformer, which really came in and kind of revolutionized the field of NLP. And since then, there have been a lot of different models that have been created, many of them based upon Sesame Street characters in terms of the name. But all of these essentially share the idea that they take text, map it to this embedding space, and then have the ability to decode it in the end as well. So I'm not going to go into the specifics of those, but these are the techniques that you'll use to actually encode your documents into embeddings and into thought vectors, and then to encode your queries. And at the highest level, a transformer works by taking some text. So in this example, maybe she went for a walk outdoors. It encodes that into a vector that represents the meaning. and then and that's the encoder. And then the decoder side of the transformer can take that meaning and then translate it back out into normal text. So in this case, I might get something like, the woman went outside to walk, whereas my original input was, she went for a walk outdoors. These essentially both communicate the same meaning, more or less, but one was encoding and then one was decoding from this thought vector. Interestingly, you can swap out the decoder for maybe a decoder trained in another language. And so in this case, I've now created a translator where I'm translating from this original language to another language because my decoder from this meaning was trained on a different language. But in the search world, usually we don't use the decoder part of the transformer. We focus mostly on the encoder, where my documents coming into the search engine get encoded. Those encodings get saved into the search engine, and then my queries at query time also get encoded into the same sort of thought vector space. And then I use the similarity between them to understand the to understand how related the items are. And so going back, just to wrap up here, that's a lot of information to communicate, but hopefully it gives you a very broad perspective of the field of search, sort of like starting from the beginning where you're working with an inverted index and doing text matching, all the way to reflected intelligence and trying to automate the process of having your search engine learn relevance from your users and crowdsourcing that relevance ranking. And then this notion of understanding user intent and really combining an understanding of your content, of your user context, and of your domain context to really get at an understanding of what your users mean given their context and what they're looking for. And this thought vector notion is really just another way to accomplish the same thing. Whereas with the inverted index and that knowledge graph example I gave you, we were dealing with terms and matching on terms and categories. Whereas in this thought vector space or dense vector search, which is often called, we're mapping into a numerical space and doing calculations there. Or you can do a hybrid where you do some things based upon keywords and some things based upon those thought vectors. Either way, these are sort of the techniques that are leveraged in search engines to understand your content, understand your users, understand your domain, and ultimately bring back the most relevant search results as quickly as possible for people running search against the search engine. So with that, I will stop with the presentation, and hopefully looks like we've got some questions. We would love to take those.
Great. Yeah, there's some questions coming. I've answered a few. I leave 4 for now, at least. All right, now, are you able to see the questions, or do you want me to read them off, Trey?
Why don't you read them to me, if you don't mind?
Great. Well, I'll start with John Tardy because it's a familiar name. I appreciate it, John. I think John's been here every single week, so glad to see you coming back. But anyways, he asks, I once had to match company names from 2 different sources where exact matches were rare. I ended up manually coding some of the strategies you mentioned, for example, TF-IDF. Have you ever seen a search tool used to solve this type of problem?
Match company names from 2 different sources where exact matches were rare. I ended up manually coding some of the strategies. Yeah, so if you think of within the search engine, obviously, if the company name has multiple words, you can use the search engine to, match on, 1 or 2 or 3 of the words and not the entire text. That's just a common feature out of the box with the search engine. You also have the ability to do edit distances, both on, terms themselves and appearing in different orders and phrases, as well as if there's maybe like 1 or 2 characters that are off on a term, you can actually search the index for any term that is, off by 1 or off by 2 or off by 3 characters from what was typed in. So you can sort of get fuzzy on, do I match all the words, as well as fuzzy on, do I match the words as phrases, as well as fuzzy on, for each of the words, are there potential other spellings that could be leveraged? So absolutely, if you're trying to match in those terms, you could probably do it pretty quickly out of the box with a search engine without having to write any code, just by issuing some queries, for sure.
Great. Yeah, and then Manny Kandan asks, how does iPad how would iPad match with iPad R? Because both terms look different to a search engine.
Okay, yeah. So if you remember back to the text analysis section at the beginning where I talked about when documents go into the search engine, they run through that analysis process. The analysis process determines how the tokens are represented in the index. And so iPad R with IPAD parenthesis R parenthesis if it's all one word, that analysis chain I showed you earlier would actually take that and split it on the parentheses and give you iPad and then R is a separate word, and it would ultimately end up throwing the parentheses away because it would see them as noise. And so what would actually go in the index would be the term iPad and the term R. Now R itself is not going to be meaningful and nobody's probably going to search on iPad R, but if they did search on iPad R, they would match, that query would also map into iPad and R, and they would have an exact match on both terms. But then if somebody comes in and only searches for iPad in their query, it's still going to match that term iPad because it was indexed as a separate token. So the search engines are designed to be fuzzy in terms of their ability to match tokens and keywords from the original document. But the control of how fuzzy is completely up to you as you're configuring the search engine analysis process.
Yep. And then Roxanne's asks, vector representations are useful for relevance scoring, but it's probably not efficient to run this against your entire corpus. Presumably, there needs to be some document filtering, like set intersection, that needs to be applied first.
That is absolutely correct. Give me 1 second and I can pull up a slide that shows that. 1 second. Almost there. Okay. All right, so this is exactly to your point. So vector scoring is slow. If you've got millions of documents or even hundreds of thousands of documents in your index, heck, even tens of thousands, trying to do a vector similarity on at that scale is going to be too slow for a real-time use case. And so unlike with keyword search where you're exactly looking up the answer in the inverted index and you already know the answer, with vector scoring, you're essentially going back to doing that table scan that we talked about where databases just won't cut it because they have to literally go through every row. And so typically what you'll do in a search engine is implement some sort of approximate nearest neighbors implementation where you take you essentially try to create quantized vectors, or you try to create discrete tokens in the search engine that you can actually filter and match on to generate a representative data set that you could then score after the fact. You can rescore. So the idea here being there's algorithms, approximate nearest neighbors algorithms, which would allow you to put a token or a set of tokens on documents. You could then filter on those tokens and still get 95% of all the documents in your top, 1,000 or 100 or what have you, that you would otherwise get if you did a full vector similarity calculation across all of your documents. And so what that essentially allows you to do is a very quick filter to find a candidate set of documents, and then to do the vector similarity calculation only on those candidate documents. And the best performing algorithms are currently giving about 95 to 96% recall. So you can essentially get really good performance by applying that as an optimization. In fact, I think, never mind. So I'll stay with that. Hopefully that answers the question.
Great. Thank you. And then Sujith Joseph has a string of questions here. One is what's the best way to combine best match BM25F plus vector similarity? And then he goes on to type a little bit about his thoughts on it, but let's hear yours.
Yeah, so it depends on what you're trying to accomplish, but in this, so what a lot of people do is in the search engine, they, well, what a lot of people do when they start to go down the path of doing thought vectors and in vector similarity as opposed to traditional keyword matching is they go and they re-implement a new system. So they say like, hey, instead of using the search engine, I'm just going to build a purpose-built or use a purpose-built system just to do the similarity between the vectors. The problem with doing that is it makes it really hard to both do your traditional keyword matching and filtering and knowledge graph capabilities alongside this, this vector similarity matching. And so I think let's see if I've got a slide here. I could show you an example of doing this in Solr, which is going to be kind of hard to read, but here we go. So pardon the syntax here, because this is going to be a bit hard to wrap your head around. But essentially what I'm doing here is I'm running a keyword search for bread, again, using those examples I shared earlier. I run a keyword search for bread, and then I say I want to boost my relevance function based upon how well I match the vector for donut. So just kind of a toy example here, but what ends up happening is, in this case, instead of scoring all of the documents, I'm filtering down to only the documents that contain the keyword match for bread, but then I'm re-scoring those documents based upon how well they match this vector for donut. And so in this case, I think by default, cheese breadsticks would have come back as the first result. They both have bread in them. But because cinnamon breadsticks are a little bit more similar to donuts than cheese breadsticks are, this one got a little bit higher of a score. And so, and you can see actually the score calculation down here where I'm doing my BM25 scoring, and then I'm doing a boost based upon the extra similarity that I got from my, my vector cosine. Now, in terms of, that's like how you can do it, and you can essentially combine those functions I showed earlier for the domain specific, relevance boosts, along with these thought vectors, which can not only get you some semantic understanding, but get you an understanding of the language of the query itself, like the English language structure of the query. But in terms of practically how you would want to combine them, I think that's going to be very domain specific. Depending on the use case, you will combine all of these features in different ways. So I can't give a general answer for that.
Great. Another question from Suji says, what are your thoughts on using BERT attention weights in a query for term boosting?
You could definitely do that. Yeah, so we sort of talked about using BERT as sort of only using the encoder part of BERT to essentially generate the vector and then doing a cosine match on it. You could definitely also pull out other information, such as the attention weights, and boost on terms that way. Really, all of these language models, whether you're talking about BERT or GPT-3, which just came out beginning of June and is pretty groundbreaking. There's lots of ways to use these to interpret and infer and boost. So yeah, I think anything you can do to better understand the query and either relate it back to your domain or your users or your content. You obviously want to test it. You want to A/B test it. You want to have some other offline metrics for testing quality. But yeah, I'm worth a shot.
Great. And then he also asks, what are the best ways to mine synonyms from query logs apart from looking at query variations within a session?
Yep. Well, you've already listed the best way, which is to look at query variations within a session. I think of learning, whether it's, you mentioned synonyms, but synonyms, misspellings, phrases, any of the, even like query rewrites, any of those types of things, I would consider domain-specific understanding that you can learn from your query logs. In a lot of cases, you can learn the same information from your documents. So if I go into my documents and I find, the word manager, and then I, do like an edit distance on that to find all the other words that are, within one character. And I get a couple back that have very few characters. For example, manger, M-A-N-G-E-R, is a common misspelling for manager. If I look in my documents, I'll probably find those misspellings here and there, and then I can map them to manager. Or if I look in my query logs and I see somebody running a search for M-A-N-G-E-R, and then immediately within a couple of seconds running a search for manager, that's really the best way to indicate that a misspelling occurred, and then I can record that misspelling, and in the future when I see people type in manger, use manager instead. So that's a sort of a way to use reflected intelligence to do that. Synonyms is the same. Look in a session, see what users searched for, see what other things users searched for, and then aggregate those together, and then look at that occurring across multiple users, and you're finding synonyms in that way. One of the ways that I've worked on before for doing this is not just to purely look at the terms, like somebody searched for this term and then this other term, but to actually relate those terms back to a category that the user belongs within. So again, for kind of disambiguation, like our barbecue example. So in this case, I might say this user who is a, like we did this back when I was at Career Builder, this user who is a software engineer searched for this word and this word. And then another user who is a registered nurse searched for that word with a different word. And what that allows you to do is, instead of getting just sort of this word maps to this word, to get a contextualized understanding of, within a specific category or specific, job type in this case, what are the synonyms for this word? And then you get a sort of nuanced vector that's generated of other related words within that context. And so I think keeping the notion of context as opposed to just mining the session is important. The other thing I would recommend is, if you have content that is similar to your queries, which most people do, once you've mined those query logs, you can actually also go look in the content to make sure that those relationships exist in the content as well, to help you get rid of noise. And so often if you sort of try finding synonyms, misspellings, what have you, both in your signals or your query logs, as well as in your documents, and then look at where you find them in both, that's going to get you a really nice clean list. And then the last thing I'll mention is that in addition to just mining these things within a session, often it can be useful to look not just at the queries, but also on at the documents that the users interacted with after issuing those queries. So you might be able to learn, again, that a user ran this search, and that search resulted in them clicking on these documents. And then what you can do is relate the terms in those documents back to that original search, and potentially find synonyms that way, by understanding that word that was searched for, even if there weren't other words in the session, most of the people, when they searched for that word, found documents that contained these other words. So those are a couple of techniques I think you could apply.
Cool. Thanks, Trey. There's a few more coming in just with time. So Alexander is asking, what do you think about the future of bitstring signature algorithms like Bitfunnel?
What do you think about the future of bitstring signature algorithms like Bitfunnel? I do not know enough about that topic to answer intelligently now. I'll have to go look it up.
Yeah, me either. I'm going to start Google searching right now. But, Alexander.
Sounds interesting. I'll look it up.
I would say join the Slack channel if you don't already, Alexander, and I'll make sure to share out a link to that right now. But let me do some research, and we'll see if anyone in the community is familiar with Bitfunnel.
Oh, that's Alexander. I know. Hey, Alexander. I know him, but I got to go look up what he's talking about.
Great. All right. So then we have a question from Carlos. Using search to vec to find synonyms, some companies use the results to expand queries. Should these synonyms that are discovered be added in the index or applied in the search?
It's a great question. So I tend to prefer techniques that do query time expansion and interpretation of queries as opposed to jamming extra content into documents. That's not to say that there's not use cases for enriching documents as well, but my fundamental assertion here is that because a query needs to be interpreted within the context of a user and a domain, not just the raw content, that whenever you enrich documents with this additional information, you're essentially choosing a specific meaning of terms and phrases and what have you. And so I prefer to leave the content in its sort of natural, semantic order, and then at query time, interpret the query, potentially leveraging that content to understand context like we showed earlier, but then to adjust the query to get at the content more appropriately, as opposed to predetermining the meaning of the content in any context. There's some value in, on a document by document basis, choosing a meaning, and then at query time being able to choose the same meaning and match. So definitely it's a valid approach. But it would depend on the use case. But I would say 80% of the time, I would go with a query expansion over a document expansion.
Great. And then we do have one more technical question, which will be the last of them. And then I want to open up the door for, a more personal question as well for, your Searchkernel, as well as be able to maybe promote some of your books. But for the final technical question, Sujith followed up with, wants to hear your thoughts on using extractive summarization of docs against queries, for relevancy.
Extractive summarization. I don't know if extractive summarization is a specific term that I should know, but I'll interpret this as taking a document and extracting the meaning out of that document and then using that document as a search. Essentially a form of content-based recommendation. Sujith, if that's a misinterpretation, please let me know. But so very much, this is a great way to do matching. So I mentioned collaborative filtering earlier, and the ability to take user interactions with documents and to then match based upon what other users had done. The collaborative filtering, the benefit is the algorithm doesn't have to understand anything whatsoever about your documents or your domain. It just purely matches based upon what other people have done. The downside is that you have the cold start problem, which is that until people actually start interacting with your documents, you can't recommend them. You don't know what they're related to. So the other way to do recommendations, or one of the other ways, is leveraging the content itself in the document. So this can be attributes or structured information that have been stamped on the documents, or this can be the text as well. You can essentially take a document, extract out the terms and phrases that are most semantically meaningful, either in the text field or in the title or in just across all the fields, and then ultimately, like we did with that example with Jane earlier, where we sort of turned her profile into a query, you can do the same thing with a document, where you take the document, you summarize it and extract out the meaningful features, you turn those into a query, and then you go match and do matching and ranking based upon that. And that tends to work very well. It doesn't struggle with the cold start problem. And often you can build hybrid content and collaborative filtering based recommenders using that. And you can also use those techniques to essentially allow somebody to upload a document and immediately, use the document as a search instead of having to type in a query explicitly. So it's a very, it's a good approach. I've done it before and it works quite well.
Great. Well, with that, I think this is kind of perfect timing to for our last question from Shyam Sunder. Can you talk about your new company, Searchkernel, and its products and services?
Sure. So yeah, just started Searchkernel not too long ago. It's a search consultancy and software development company. So we essentially for companies who are trying to implement search technology, we will work with them, either sort of an advisory or in consulting, doing workshops, doing trainings, or coming in and trying to assess and analyze, if they have a pre-existing search application, what's working and what's not. We have a particular focus on relevancy, like we've talked about today, and also in some cases we'll do some software development and licensing for some products that we're in the process of building, if we can help some companies build those out, while also building something that we can sort of add to our portfolio for later. So bandwidth is pretty tight. It's mostly me, got a couple of other people working with me, but it's if you've got an interesting problem, I would love to chat. Hopefully we can help. If not, certainly happy to leverage my network and help get people the help they need. But yeah, I mean, as you can tell, I'm very focused on search, focused on relevancy, and a lot of really cool stuff going on in this domain. It's a fantastic field within data science to be working in. And so, that's pretty much it. So if you'd like to talk more, you can reach me by email. It's just Trey, Trey, at searchkernel.com. And otherwise you can find me online, and would love to chat.
Great. Well, Trey, I appreciate it. This is very helpful and insightful as well. It's awesome when you kind of look at the participants and see that everyone stayed on through the whole content. So you kept everyone interested. But really, I do appreciate it again. And I hope everyone enjoyed the content. We will share out the recording, and if Trey's okay with it, we'll share out the slide deck as well. We'll post in the chat channel, and everyone should be able to receive an email for those who registered for this event. And with that said, we'll see you next week. So Khalife, the founder of Southern Data Science Conference, and also the lead data scientist at Home Depot, will be giving a presentation on recommendation engines. So tune in next week. It's the final one in this particular series, but hopefully we'll keep this going in the future and with more. Great.
Awesome. Thanks, Brian.